Welcome back. I have a beam here that is subject to distributed load, a point force, and a couple moment. The support at point A is called fixed support. It resists both translational and rotational motion. It's simply welded into the wall. You can neglect the weight of the beam. And so your task now is to identify and find the reactions at point A. Good luck. Try doing it yourself first and then see the solutions in the next video. Thank you. Welcome back. Let's now find the reaction forces for the beam for this new configuration. Note that if we only consider the beam in our free body diagram without the BC2 force member, then force B at point B is also one of the reaction forces, just like AX and AY. And of course here you had this 600 Newton force, here 800 Newton force, and here a 900 Newton meter couple moment. Let's use the rigid body equilibrium principles to solve for AX, AY, and B. Let's first decompose this B force. You can see that you have 2 meters from A to B and 1.5 meters from A to C. And so you can describe the direction of this B vector, which is parallel to the BC member, in the following way. This is your B force. Here I'm going to have 2 meters. Here I'm going to have 1.5 meters. And then here I will have C, and then C will be square root of 2 squared plus 1.5 squared. It will be 2.5 meters. It means that Bx equals B times 2 over 2.5, which is 0.8 B, and By equals B times 1.5 over 2.5. That's gonna be 0.6 times B. Next, we will apply the rigid body equilibrium principles. The sum of the forces in the x direction must be 0. And now, according to this free body diagram here, in the upper left corner, I have AX plus BX. It will be 0. In other words, AX plus 0.8B, that will be 0. Then in the y direction, I have AY plus BY minus 600 minus 800. That has to be 0. So AY plus 0.6 times B minus 1400, it equals 0. And then the sum of the moments about point A must be 0. So now you have By times 2 minus 600 times 1 minus 800 times 4 minus 900, and that will be 0. In other words, you will have 0.6 times B times 2 minus 4,700, which is 0. If you had Bx and By in the equations, then you would have had 3 equations and 4 unknowns, Ax, Ay, and then Bx and By. And then you would not have been able to solve it. But since you know the direction of the B vector, you could express Bx and By in terms of B, and now you have 3 unknowns and 3 equations. You have Ax, Ay, and simply B for your unknowns, so you can solve for them. In the moment equation, you have 0.6 times 2 times B, that's 4,700. B equals 4,700 divided by 2 times 0.6. That will give you 11750 over 3 newtons. Then from the second equation, you have AY equals 1400 minus 0.6 times b, which is this one, and that's your AY, minus 950 newtons. And then from the first equation, AX equals minus 0.8 times b, which gives you this result, or this one here. And there you go, you have the answers. Note that AX and AY are negative. You already know what that means. It means that on the free body diagram, our assumption for the directions of AX and AY was wrong. In reality, AX points to the left and AY down. And it's especially intuitive for this AX force. It needs to counter BX that itself points to the right. Also, since BY is the only force that creates a counterclockwise moment about point A, it will be BY times 2 or 0.6 times B times 2, which is 4,700 Newton meters counterclockwise. And as you can see, in the previous case, with a fixed support and without this BC rod, the reaction moment, MA, was also 4,700 Newton meters counterclockwise. Thank you very much. Welcome back. Let's now identify and find the reactions at point A. As mentioned before, now you have fixed support. The beam is fixed to the wall in such a way that at point A, the translational and rotational motion is restricted. It means that at point A, you have two reaction forces, AX and AY, and a reaction moment, MA. We will assume that it's counterclockwise. If we are right, MA will be positive. And if we are wrong and MA ends up being clockwise, then it will be negative. The first thing that we can do is to replace this distributed load, 300 newtons over meter, by an equivalent point force. And you already know how to do it from the previous course. You have 300 newtons over meter times 2 meters. It's this one here. The meters get cancelled out. You will have 600 newtons. And since the distribution is uniform, you need to put this 600 Newton point force in the middle of that distribution. And then this is your 800 Newton force. This is your couple moment. And the reactions. And then here you have 2 meters. And now it's just a matter of finding AX, AY, and MA using the rigid body equilibrium principle. We first do it in the x direction with the forces. You only have one force in the x direction, AX, and so it has to be 0 because the total sum of all the forces in that direction must be 0. And it's the only one, so it must be 0 newtons. Then in the y direction, you have these forces, and so right away you know that AY equals 800 plus 600, that's 1,400 newtons. Finally, I'm gonna take all the moments about point A, and it must be 0. I write here M total A because it's a different thing than this one here, MA. This one is one reaction moment at point A that does not allow this beam to rotate in either direction. But then you have to sum up all the moments, and so I'm going to put here M total A. And so we assumed MA to be counterclockwise, so it's positive, then minus 600 times 1, so it's this force from the distributed load, and it's 1 meter away from point A, minus 800 times 4. So that's this force times this 4 meter moment arm. And then you have a clockwise couple moment here as well. So it's minus 900. And all that must be 0 And so from that, you can see that MA equals 600 times 1 plus 800 times 4 plus 900, and that's 4,700 Newton meters. And there you go, you have your answers. AX equals 0 newtons, AY equals 1,400 newtons, and MA equals 4,700 Newton meters. But now, it might happen that this support at point A is strong enough to cope with the reaction force AY, but not strong enough to cope with the reaction moment MA. It's like, imagine that you're holding a bag. That bag has a mass, so it also has force of gravity Fg, which points down. In one case, you're holding it closer to your body, in another case, further from the body. In both cases, you have the same reaction force, Ry, that counters Fg. However, intuitively you can feel that it's harder to hold the bag in the second case, when it's further away from the body. That's because, in the second case, Fg generates a greater moment about the point where your arm connects to the body. So your muscles in that connection point need to generate a bigger reaction moment because you have a bigger moment arm here. That's why it feels harder to keep the bag in equilibrium in this second case. And if you have a very long arm, then you might not have enough strength in your muscles to keep the bag in equilibrium. The same logic can be applied to our beam example. It might happen that the fixed support is too weak to cope with this reaction moment, 4,700 Newton meters. In that case, the structure might collapse, and that would be very bad. Very, very bad. Now, one solution would be to make the fixed support stronger. But there is another way. I can change the support at point A and put a smooth pin there. That, of course, means that you will lose the resistance to rotation at point A. So you will only have AX and AY for your reactions. But that's okay. You will compensate that by using a rigid rod that is connected to the beam B with a smooth pin, and then the other side of that rod is connected to the wall at C, also with a smooth pin. So here, these ones will be your reaction forces, Cx and Cy. This rigid rod, BC, is called a two-force member. A two-force member is a structural element that has one force applied on one end of the member and another force on the other end of the member. And the thing about two-force members is that in order for them to be in equilibrium, meaning that they cannot translate nor rotate, three conditions must be met. First of all, both forces on both sides of the member must have the same magnitude. So F1 equals F2 equals, let's just call it F. So they have to have the same magnitude. Secondly, both forces must be in the opposite direction. These two conditions will keep the member from translating. And thirdly, both forces need to have the same line of action. That condition will not let the member rotate. And that's the case here. In here, these three conditions are met, so the member is in equilibrium. And that's also the case with our BC member. If we mentally separate this BC member from the rest of the structure, then the BC member, in this case, is in compression. it's compressed. Since the entire structure is in equilibrium, the aforementioned three conditions are met, and thus B equals C in terms of their magnitudes, they're opposite in direction, and they have the same line of action. Due to Newton's third law, the beam will also experience the force B at pin B. It will have the same magnitude, and it will be opposite in direction to this force that is applied to member BC from above. And then also here, the member BC applies a force C to this pin at point C. And this B force will create resistance to rotation for the beam. If you decompose this vector, then you will have Bx and By, and this By, it has a 2-meter moment arm till point A, and so while your 600 Newton and 800 Newton forces create a clockwise moment about point A, together with this 900 Newton meter clockwise couple moment, however, By will create a counterclockwise moment about point A that will neutralize all the other clockwise moments. And if you're wondering if this configuration really keeps the structure from rotating about point A, then remember, both the beam and the BC member are assumed to be rigid. The BC member connects points B and C. If I start rotating the main beam in this way, for example, or in this way, then the distance between the points B and C would start changing. Then the length of the BC rod would have to change as well, but it can't. It's rigid, remember? Furthermore, you have a smooth pin support at point B as well. It means that while it does not restrict rotation about point B, it does restrict translation in all directions. That's why, if the BC rod is strong enough, it will not let the main beam to rotate. And now, your task is to find the reaction forces AX and AY and the force B at point B on the beam for this new configuration. Again, you can neglect the weights of the beam and the two force member. So good luck, try it out by yourself first, and then see the solutions in the next video. Thank you. Welcome back. I have a structure here that is in equilibrium. At point A, you have a roller support that can move along the ground, and the motion is restricted normal to the surface. The support A, the roller, is attached to the structure via a pin. And then at point B, you have a smooth pin support. You can neglect the weight of the structure. It is also subject to a 390 kilonewton force and an 800 kilonewton meter couple moment. You have the direction of the force vector and all the necessary dimensions in the image. And so, the task is to identify and find all the reactions at points A and B. So good luck, try it out by yourself first, and then see the solutions in the next video. Thank you very much. Welcome back. Let's now identify and find our reaction forces at point A and B. Let's start with a free body diagram. At point A, you have a reaction force A normal to the surface. And then at point B, you have Bx and By as your reaction forces. No translation can happen there. However, rotation is possible. That's why you don't have a reaction moment there. At point A, you don't have it either. We can decompose this A vector like this. The A force equals and then this is the x component, and this is the y component. In other words, this is AX, and this is AY. These are the reaction forces. We have identified them. Let's now use the rigid body equilibrium principle to find them. So this is forces in the x direction. You have the x component of the A vector, bx, and then minus 390 times 5/13. And that must be 0. So this final term, that's the x component of this 390 kilonewton force. This ratio here, 5/13, it's this 5 over this 13. It gives you the horizontal component of this vector. Then in the y direction, I have this equation. Again, the final term, it's now the vertical component of this 390 kilonewton force. Finally, let's take the moments about point B, this point here, sum them up, and the result must be 0. So I have 800 here, which is this couple moment here. Then the vertical component of this applied 390 kilonewton force, it gives you a 0 moment, because it has no moment arm. It goes through point B. However, the horizontal component does have a moment arm. It's 3 meters, and that will give you a counterclockwise moment. So plus 390 times 5/13. That way I obtain the horizontal component of this force, and then times 3, which is the moment arm. Then you have minus AX times 3 and minus AY times 12. And all that equals 0. Now AX, it's A times sine 30 degrees, or simply 0.5 times A. Then AY, it's square root of 3 over 2 times A, and then you replace them in the last equation as well. I chose to take moments about point B because that way, in the third equation, I will only have one unknown, which is A. And so, these are your equations. You have 3 of them. And since you have expressed AX and AY in terms of A, you also have 3 unknowns. And so, I'm going to take the last equation and write it like this. I will have all the terms with A on one side of the equation sign, and then everything else on the other side. In the end, I can express the entire thing like this, or simply like this, which is approximately 105 kilonewtons. And now, I'm going to take the second equation, and I will find By like this. By equals, and then all this, you have A here, but you already know your A, so in the end this is your By. You can cancel this 2 here, and write here 1250, and so you will have approximately 269 kilonewtons. Finally, we'll take the first equation to find Bx. I will write it like this. Bx equals all this, which is all this, and it's approximately 97.4 kilonewtons. And there you go, you have your answers. All the support forces are positive, which means that your assumption about their directions was correct. Thank you very much. Welcome back. I have a wall here. On the right of that wall, you have soil that exerts some kind of pressure on the wall. You can see it in the image per unit length. You see kilonewtons over meter. You can see that at point A, you have 310 kilonewtons over meter. The height of the wall and the depth of the soil are 6 meters both. On the left side, you have water. Its depth is 4 meters. The density of water is 1000 kilograms per cubic meter. You can Assume the gravitational acceleration to be 10 meters per second squared. In reality, it's closer to 9.8 meters per second squared, but here let's make it easy on us and let's say that g equals 10 meters per second squared. The width of the wall is 2.95 meters. The soil pressure in pascals and the depth of water are both constant per width. This wall between the soil and water is attached to the ground with a smooth pin at A. To ensure that the wall does not rotate counterclockwise about point A due to soil pressure, at point B we have a cable support. Its other end, point C, is connected to another fixed wall. In addition, the mass of the wall that separates soil from water is 800 kilograms. You can assume uniform mass distribution and constant g, and you can neglect the mass of the cable. You can also see that point B is vertically 0.5 meters from point D. And now, your task is to identify the reaction forces at points A and B and find them. Think about what kind of resistance to motion cables can provide you with. Good luck, try it out by yourself first, and once you're done, the solution will be in the next video. Thank you very much. Welcome back. So let's now identify and find the reaction forces at points A and B. Let's first analyze the pressure distribution due to water. In Statics 1, you learned about the Pascal's law. You learned that water exerts pressure on an object normal to its surface. The magnitude of the pressure depends on how many meters underwater you are. The formula was the following. Pressure equals the density of water times g times your depth underwater that you start counting from here. Z is positive as you go down. And that will of course be in pascals or newtons over meter squared. So rho W was the water density, 1000 kilograms per cube meter. G was the gravitational acceleration. We assumed it to be 10 meters per second squared. And so what you have is pressure equals 1000 times 10 times Z, and that's 10 to the power of 4 times Z pascals. So that's your pressure distribution due to water. Note that this is in pascals or newtons per meter squared. It's the pressure that is applied to the entire surface of the wall. However, the depth of water does not change when you go in the direction of the width. It means that we can easily obtain the equivalent distribution per unit length in newtons over meter that will act vertically in the middle of the wall. That vertical line along which the pressure distribution per unit length acts, it's 1.475 meters from one side and from another side. To get that distribution per unit length, you only have to multiply this pressure in pascals by the width of the wall. So let's call it WW. This is the pressure distribution per unit length for water. It equals pressure in newtons over meter squared times 2.95 meters. I make some unit cancellations and I'm going to be left with 2.95 times 10 to the power of 4 Z newtons over meter. And now, on the other side, we have pressure from the soil, but that was already given in pressure per unit length, in this case, kilonewtons over meter. It also acts along the vertical line in the middle of the wall. That's because it was said that the soil pressure in pascals or newtons over meter squared does not change with the wall's width. Now at the location, which is 4 meters underneath the water, we can calculate the pressure per unit length for the water. So it's going to be WW at Z equals 4 meters. That's going to be 2.95 times 10 to the power of 4 times 4. It will be 118,000 newtons over meter, or equivalently 118 kilonewtons over meter. And so that's the pressure distribution per unit length here at A. So now in this image, instead of representing the pressure for water in pascals, I'm going to represent it per unit length. And so here at A, I will have 118 kilonewtons over meter. Welcome back. Now that we have our pressures per unit length on both sides of the wall, we just need to go from kilonewtons over meter to the equivalent point force representation. You already know how to do it from Statics 1. You get the areas of those distribution triangles. From the soil, you have Fs equals 310 times 6 times 1/2. That's gonna be 930 kilonewtons. And then from water, you have Fw equals 118 times 4 times 1/2, 236 kilonewtons. So we have the point forces, but of course, we also have to apply those point forces in the right locations to make this representation equivalent. From Statics 1, you know that when you have triangle distribution, and let's say that the length of the wall is B meters, then the center of pressure of this triangular distribution per unit length, it's B over 3 meters from this side and 2B over 3 meters from this side. And that's where you have to put your point force. So if this is our wall here, then for the soil, the force Fs will be placed 2 meters from point A in our free body diagram. That's because the total length here is 6 meters, and 1/3 of 6 meters is 2 meters. And then from water, I'm going to place Fw 4 over 3 meters from point A. That's 1/3 of 4 meters. In addition, the mass of the wall is 800 kilograms. That means that the weight or force of gravity that the wall experiences, its Fg equals m times g, which is 800 times 10, which is 8,000 newtons, or equivalently 8 kilonewtons. Since the wall's density and the g are assumed to be constant, the center of gravity, or CG, is gonna be in the middle of the wall. So this point here is gonna be 3 meters from point A, and also from point D. Finally, let's talk about the supports. At point A, you have a smooth pin support. So you have two reaction forces, AX and AY. But now, you also have a cable support at point B. The thing with cables is that they only resist motion along the cable when it's in tension. So you have a force B that acts along the cable, and it's 0.5 meters vertically from point D. Note that this entire configuration works because the soil applies more pressure from the right than water from the left. Because of that, the cable is in tension, and it keeps the wall from falling on the water. Also, because of the fact that the center of pressure of the soil is above the center of pressure of water, that also makes the wall want to rotate counterclockwise. And the cable helps prevent that because it's in tension. This cable would have been useless if you had stronger pressure from water, making the wall want to rotate clockwise about point A. Then the cable would be in compression. However, cable support cannot resist motion when it's in compression. In that case, instead of a cable, you could put a solid rod there. A solid rod can resist motion when it's in compression. So in conclusion, you have to be careful when you use cable support. You must be sure that the loading situation does not change in such a way that the cable ends up being in compression. It can be very dangerous. And so this here, that's our free body diagram. Positive x is in this direction, positive y in this direction. But now, let's find our ax, ay, and b. And we're going to do it using rigid body equilibrium principle. So first of all the forces in the x direction, you have this equation. Then all the forces in the y direction, you have this equation. And then I will calculate all the moments about point A due to convenience. So that's the equation. So here I can write ay equals fg, the lines of action of ax, ay, and fg go through point A, so they produce no moments about that point. Also note that the moment arm between B and point A, it's 6 minus 0.5 meters, so it's 5.5 meters. Since we know what our Fg is, I can also say that my Ay equals 8 kilonewtons, which is 8 kilonewtons upwards. Then from the third equation, I can write 5.5b equals, and then all this, and then I can get rid of 5.5 if I put it here. So b equals all this, or this, which is approximately 981 kilonewtons. And then from the first equation, you get ax equals all this, which is all this, which is this one, or approximately 413 kilonewtons. And there you go. You have your support forces. They are all positive, which means that your assumptions about their directions were correct. Thank you very much.